Okay, so I'm going to give a talk about machine learning for PDEs. So this talk is sort of an idea dump, and it may not be very coherent, but hopefully at least you'll get the ideas. And Yohai is here, right? He did 99% of the work. Stefan. Yeah, anyway. So for the majority of this, so when I get stuck, and at some point, Yohai, if I goes wrong, I'll just get you to give this talk. And so that's it. So I'm going to start with general nonsense. So PDEs, of course, pervade the physical sciences. That is, from fluid mechanics to optics to whatever. We're all taught when we're young that the leap from ODEs to PDEs is that PDEs have an infinite number of degrees of freedom, whereas ODEs only have a finite number. And the argument for why there's an infinite number of degrees of freedom is that, of course, there's an equation at every point in space. You're trying to enforce Newton's laws at every point in space, so there's an infinite number. But we all know that that's sort of a lie. I mean, PDEs don't really have an infinite number of degrees of freedom. I mean, in fact, I would argue that applied mathematics, the subject that some of us pretend to work on, that the historical goal really is precisely to characterize the finiteness of the number of degrees of freedom that a PDE has. So subjects that are dear to some of our hearts, like boundary layer theory, multi-scale methods, all of these things are about taking the solution to an infinitely number of degree of freedom system and finding ways to reduce it to make it so that you can think about it and apply it to the world in understandable ways. And the sort of thesis of this talk is, and this research program, is that machine learning really offers new ways of parameterizing, of reducing the number of degrees of freedom and changing the way you compute. And we're trying to do this in a number of different ways. So this talk has 3 vignettes. The first one is the longest, but the second 2 maybe I'll get to go through too. And these are just different ideas that we've sort of thought about for how one might be able to use machine learning to help with PDEs. So the first is what you might call data-driven coarse graining. The second is something about representing solutions. It has similarities to some of the talks this morning. And the third this is one that I'm actually quite interested in, but is sort of developing new imaging modalities. And anyway, we'll see how far I get. So, okay. So, and then there are all these people who helped. So there's Yohai. You look a little blurry in that picture. And there's Stefan and Jason at Google who helped, who worked on the first project, and then I'll get to the other people when we get to it in the topic. So data-driven coarse graining. So the sort of the way that this goes is these are supposed to be simulations. These are simulations of the weather, and here's a simulation of turbulent convection. And what you're supposed to see is that that there's just tremendous complexity. So you're supposed to, fluid mechanicians stare at these things and it makes them happy. And this sort of tells you about all of the grid points that are used. So this is a simulation with 10 to the 8 grid points. Can you imagine? And of course, the reason that this is a problem is that the computational cost scales with the number of grid points. In fact, it scales like 1 over some power of the grid spacing. In 3 dimensions, 1 over delta x cubed for the number of points, and then you have to divide by another power of delta x because of time stepping. And basically, I think that this is a fair statement. This is essentially why we have supercomputers. If you want to basically do a larger calculation, you need more grid points. So now you should get a bigger computer. And basically, the situation is that these are sorts of computations. I think I'm not misspeaking. They can be done once, right? Like you do it once, it's a shot, and that's it. You can't actually use it to do science, which requires that you do it more than once. Let's see if I can get the minutes. So I haven't had to advance these things. Oh, I see. Okay, now of course and so the way that such equations are solved, and you all know this, but I just want to review it, is that what you're supposed to do is discretize the equation in space. At every point in space, you're supposed to, give imagine that there's some value of the function, then you're supposed to turn it into a set of ODEs to solve. Now of course, as we all learn when we take or teach numerical analysis, there are sort of an infinite number of ways of reducing PDEs to ODEs with spectral or whatever, which are happy, I don't care what your method is, but at the end of the day, you're basically just, replacing you're just representing degrees of freedom. And what we also know is that if you look, for example, at the state-of-the-art weather model, look at the simulation of a hurricane, that things are traditionally under-resolved. In fact, it's essentially impossible to simulate anything. We were just having a conversation about the validity of CFD. And I mean, you just can't, this is a game which has never been won. I think that's fair. Anyone can yell at me if you disagree, but this is a game which it's even worse than that. It's not only that it's never been won, it's not even clear it's winnable. Like, there's one of these things, like we can wait 20 years and see if it gets better, we'll have bigger computers. Okay, so the way that people generally deal with this, and I'm assuming many of you know more about this than I do, is what you do is you say, well, I can't resolve the flow. I can't do a direct numerical simulation. So what I'm going to do instead is I'm going to invent another equation, which reminds me of the initial equation, except that somehow it incorporates the unresolved degrees of freedom. And applied mathematics is a subject in which people have spent their careers inventing ways of changing the equation into effective equations with effective viscosities or whatever to try to basically make the thing represent degrees of freedom that you can't resolve. Once you do that, you then take the equation that you have, where you spend your tireless effort on these terms. You then, of course, discretize the new equation, and now you yet again have another set of discrete equations which you put into your computer that you can solve with physics-based coefficients. And these are basically curve-fitting exercises. They're curve-fitting exercises with a strong scientific basis, and I don't know, I guess this is a room full of people who drank the Kool-Aid about machine learning, although probably everyone hasn't, but I don't know about you, but like, everyone hasn't drank the Kool-Aid, and you know, the one period, I mean, seriously, you're fitting these math, but you know, physics science, there's a lot of fitting going on in science, and so there's real opportunity to think about how to do it better. And I mean, just as examples, I mean, I don't know, if you look at COMSOL, like, there are many models, like, there are all these models, like, different opinions, and this is why there are supercomputers. So, okay. Okay, now, so our idea, and I want to make sure, okay, so our idea is the following. So PDEs, in reality, there's a low-dimensional manifold where solutions live, even though they have infinitely many degrees of freedom. And this is a field that in mathematics and applied mathematics, people have also spent a lot of effort trying to measure the number of degrees of freedom that what's called the inertial manifold might have. So for example, here's a famous paper by Andres Titi, in which he tried to estimate the dimension of the inertial manifold of the Navier-Stokes equation. This is the actual solution manifold, which of course increases in dimension as a function of Brenner's number, but this is a mathematics paper that tries to bound the dimension. So what no one has ever tried to do, though, to my knowledge, although this is actually not quite fair, let me back this up. So what is much more difficult to do is to actually parameterize the solution manifold, to actually discover what is the parameterization of the finite dimensional manifold that we know the solution is on so that you can actually compute with it. And so basically, we believe that machine learning gives you a new way of doing this. In fact, there are many ways of doing this with machine learning, and I'm going to tell you about exactly one of them that we've been going after. And this is sort of part of the general theme that in general, whenever in life you have something which is ad hoc, and I would argue that despite our thinking that many of the methods of mathematics and applied mathematics are not ad hoc. They actually, if you think about them, they are. Machine learning should basically be a way of getting rid of these approximations in favor of something else, and whether or not something else is better or not is one has to see, but that's basically the idea. So, okay, so is that was my introduction. Okay, so let me just give you a thought. So, I mean, if you look at hurricanes, then, I mean, there are patterns that occur again and again. Right? I mean, like, there are things all the same. You might think that what we could do is build a numerical method that basically respected the patterns that exist in the data. Like, so traditional methods don't do that. The goal of traditional numerical analysis is to invent methods that are general, that work for any equation. That's what we teach our students. We all these Taylor expansions and whatnot for any of you who give these lectures. Oh, it converges, whatever. Suppose I want a numerical method that basically respects what happens in a particular equation, then maybe I can relieve myself of that burden and do much better. Of course, the price for that, there is a price. The price is one will end up with numerical methods that are equation specific. But, on the other hand, there are only a couple of equations that we care about. Okay, so this work actually was inspired in a way, this approach was inspired by work in the computer vision community on what people call single image super resolution. So here's the deal. So you take an image, like you take a picture on your phone, and then, of course, the picture has a large number of pixels in it. So if you want to store it, a good idea is to downsample it by like just representing every other point or something like that. And now, now it's lower to store. But what you would like to be able to do, of course, is reconstruct the original from the downsampled image. Now, one way to do that is to just use cubic spline interpolation. You simply, an image is just an RGB map. There are 3 matrices of different colors. You simply use cubic spline interpolation to interpolate what the image, the downsampled image looks like. And this is bicubic interpolation. So this is the original. And you'll notice that this still looks blurry. This is basically what every numerical method does, is it's using some sort of whatever interpolation to do this. Whereas on the other hand, if you instead train a neural network, you can do much better. And the reason is that the neural network basically is trained on a large set of images which have features that are like that of the original, and that it somehow learns enough about the patterns that it's better able to fill in the missing points. Now you then say, well, what is the large set of images that you're training this on? And if you were in charge of figuring out how to make these algorithms work on phones, at least I could imagine that it would give you nightmares, basically, over whether you've actually included them all. But if you're instead in charge of solving PDEs, it's a much better game to play, because the solution manifold is finite. I already told you that. You knew this. And so it's a much better place to go for. And so this work was really based on the question of whether or not it was possible to somehow use these methods, these types of ideas in our context. So let me just give you an example. So imagine I give you a bunch of solutions to a PDE. And I'm not going to tell you which PDE it is. In fact, I could ask you to guess, but you couldn't, because there's an infinite number of PDEs that give you solutions. So let's remember how we do this. So what we do is we choose grid points. So I've chosen grid points. Then, suppose we're only given the solutions on the coarse grid. So we would like to evolve this in time. You know the PDE. So now what you need to do typically is to estimate the derivatives at all of these points on the solution. You need to estimate the derivative. So what are you supposed to, and that's the only way you can advance it, because the PDE says the UDT is some function of the solution and the derivatives. So what we teach our students is that, well, if you want numerical methods, you should use some sort of polynomial interpolation. So you interpolate polynomials through the points, and you all know the drill, and then you use that to compute the derivatives. And of course, this is totally wrong, and this is why the thing, we should use 10 grid points per, whatever. This is where this rule of thumb that we all grew up on came from, because you damn well better, put enough points in there so that this doesn't happen. So you better not under-resolve it. So that's the thing. So, and this looks terrible compared to the original solution. But now suppose I told you, and you probably guessed, that these are solutions to Berger's equation. So if I told you they were solutions to Berger's equation, and Berger's equation, of course, is dissipative, and so to make this interesting, we need to include some sort of a forcing function to keep the things going on. And then instead what I told you was, for those of you who know everything about Berger's equation, of whom there are probably some of you in the room, you then know exactly what to do. But if you don't, let's just suppose you don't, then I can just give you large numbers of examples of solutions to Berger's equation. I'll just generate lots of them. And then I'll tell you, here are the grid points, here are all the curves that I have. Can you please now predict the derivatives? And the claim is that you're going to do much better. You can basically now treat this as a regression problem. You have a training set, namely the training set is the set of solutions that you've generated numerically. Computation time in the modern era is free, and so therefore you can just generate lots of them. You can downsample that onto the grid points, and then those what the answers are for all the derivatives, and then you simply build a regressor to basically using these as examples to make it work. And if you do that, you do much better. This is not a surprise. This is not rocket science. This is literally, like, if you just build a regressor, and there are a million ways to build a regressor to do this. This one I think was a sport factory machine, but whatever, right? It doesn't really matter. You just some regression algorithm to do this, and then, of course, it does much better than cubic splines, and it agrees almost exactly with this thing. So this is a different type of a numerical method. So what this part of this talk is going to be about is, yes?
But any of the solutions you showed can be initial conditions to any equation, right?
Okay, good.
So how is it specific to the Berger?
Oh, because, so I'm going to explain this, but the idea is, suppose you want to solve a PDE, Berger's equation. What you're going to do, so what we're going to propose is that what you should first do is take a small domain, and you should do very high resolution simulations of that equation. You should generate all of the features, the shocks, the vortices, whatever it is that makes you happy. You then do what I'm about to tell you, but basically it's like learn about those features, and we're then going to make a numerical method which only works for that. So I told you it's an equation-specific numerical method. But the advantage is that what we're doing is we're trading off, instead of effective equations and thinking about physics, we're going to just do high-resolution simulations to basically train. but it's equation specific. It won't work when you change the equation, you have to redo this. And so this only is a worthwhile thing again, you know, if you really care about the equations. But again, I will repeat, I think there are only a few equations that we actually care about. So this is not crazy. And also, we'll come back to this. This is a question about how you want to spend your compute resources. So this is a sort of different way.
Along those same lines, if you have an equation that has very different solutions in certain regimes, would this sort of training also potentially limit you not just to an equation but to a certain regime?
So in the same way as if you were in charge of the photo recognition thing on your phone, right, you need to make sure that your training data contains representative samples of all of the situations that you are going to do. Otherwise, this will fail. But this is true of all of machine learning. Right? This is basically This is a core problem of all of the machine learning that you can imagine. Is how do I make sure that for the amount of training data that I have, that it doesn't extrapolate, right? That I actually cover the space as well as possible. So there is this issue to think about. But this, I would claim, is the standard. Yeah.
So then it opens up the problem that we have to run a lot of simulate models input output equations. And then that leads to the problem of saying, okay, how about this balance this? So any principal solutions?
So let me show it to you first, and then we can talk about that. I agree. This doesn't nothing like this without cost. And in the end, the research program that I'm going to outline may fail. That is, it may turn out that this is not the successor to turbulence models. But this is at least an idea. And it has holes. I'm not sure I would call this a hole. That's a feature. One has to think about that. So but we will talk about it. Okay, all right. Let me now explain to you what we did. So I want to just start by just saying, so we're going to be talking about coarse grading, and I just want to make sure, because when you see the pictures that I'm going to show you of simulations, that you know what coarse grading is. You know what I mean. So this is a high-resolution simulation of an induction diffusion equation, which we will get to at the end of this talk, or this part of this talk. So this is an exact coarse grading of this simulation, in which one basically, looks at cell averages of the exact solution, and this is what, if you had an exact coarse grading, that's what it would look like. Do you see what I mean? So that it still doesn't look exactly like it because you're representing it at lower resolution, but the time dynamics is the same. So on the other hand, if you were to do this numerically, and this is just to remind you, so there are methods that you can use. There's finite volume methods, there's uplimiting, there's slope limiting, there's all of this family of methods. So if you do it that way, that is, if you take the simulation and you initialize the grid points on a coarse grid, and you then solve, then basically with current methods you have a choice of, if you make it coarse enough, either being unstable, as this one is, or being inaccurate, as this one is, because this one, numerical diffusion, has taken over everything, and that's basically what we're trying to beat. Okay, so I've already said this, sorry, but I'll just say it again. So estimating derivative is an essential approximation for numerical resolving PDEs. This discussion I'm about to give is really centered around finite difference or finite volume approximations, but I would claim that the same idea could be used for other methods if you so chose. So what we would like to reproduce, what we would like to replace are these formulas. So this is very simple. That is, instead of saying that the second derivative is given by this, we're going to replace the formula. Now you say that's crazy, you're not allowed to replace the formula, this is calculus, but my claim is that if I tell you that the solution manifold has constraints on it, I can invent formulas that obey those constraints. And so there is room here, and that's what we're going to talk about. Since this is a talk about physics and machine learning, I will talk a little bit about imposing little bits of physics on the constraint, as constraints on the models and what use it has maybe at this time. So as I already said the method, we're going to perform any high-resolution simulations. We're making a training the regression algorithm to machine learn the solution manifold and use it to time iteration. So, okay, we're given a PDE. So we're going to approximate the derivatives, the nth derivative, by a formula which looks like this. It's going to be over a stencil of capital N with capital N plus 1 grid points. So for example, the second derivative formula that I told you is this. But now we have these coefficients, alpha k sub n refers to the number of derivatives. K is basically 1 minus 2, 1 in essential. And essentially what we're going to do is to machine learn these alphas. So we're going to basically try to learn the method. So we're going to basically say that in general, these alphas are functions of the solution. So we're going to, for example, give the computer the velocity field, the function value at these 2n plus 1 mesh points, and we're going to ask it, what do you think the alphas are to get the derivative right? in the middle of this. And this is just sort of, we're getting ahead of ourselves a little bit, but we end up learning these from data. So this is a plot of the solution to Berger's equation, and I will explain where this came from in a minute, just to sort of make sure you all understand what we're doing. So as a function of space, so these are the discretization formulas for calculating a derivative. So you see there's, the derivative formula is usually positive, one minus another, right? But there are other values, and what I want you to notice is that these change. So these are resolution dependent, and they change in the vicinity of the
So
shot.
n is 3, and whether the value is slightly positive or negative, is whether that's going up or down.
That's right. That's the size of the weight. It's the size of the alpha. So basically, these discretizations are going to depend on space, and we are at every time step in our algorithm going to compute all of the weights, and then we're going to use that to basically reduce the ODs, and we're going to go from there. Okay, so this is the way that we do that, and this is a complicated slide, but this is the substance, so I should probably explain it. So you start with, remember the way numerical methods work, you start with the solution at one time and you want to get the solution at the next time. That's the game. So the next time is not supposed to be very far from the first time. So what you do is you take the function, we have the values of the function at the mesh points, right? That we find the mesh point might be such that it's under-resolved. In fact, that's the whole point. We then need to compute the spatial derivative that I've changed from alphas to c's from the last slide to this one, I apologize. We then actually, and this is a sort of physics-inspired thing. Since Berger's equation and indeed the equations that we're solving tend to be in obey continuity equations, you have to decide what you're going to machine learn. You can machine learn the derivatives, you can machine learn. So, but it is much better, and this is sort of long known in numerical analysis, to learn the fluxes. So we're going to then take these formulas and get the fluxes. From these fluxes, we're going to compute the time derivative using a formula, and then what we're going to do is now we have all of these, so when we train the model, we don't know what any of the C's are. But what we have are lots and lots of data, high resolution simulations, which we know that these are ground truth. We just spend lots of grid points on them. We simply subsample them at coarse points. We know the values of all of the derivatives and everything there, and then we simply create a loss function that essentially enforces that the numerical method is accurately representing the solution on the coarse mesh. So that's the idea. And when we train, we simply do that. So these coefficients are generated from a neural network. We use a convolutional neural network of a rather simple form. There are, at the end, and this is something you could choose to do or not, we impose polynomial accuracy constraints on the coefficients to basically make sure that the method is accurate to some order. You can do this or not, doesn't really matter. And then we train it. So how you train it, there's sort of lots of possibilities, and this came up in the talk at the beginning of the day. There are loss functions. You can invent anything you want, like now it's your turn to reinvent it. And of course, the gods of machine learning have given us tools so that we can just try everything. And actually, one of the great things about working at Google is that you can try everything. It doesn't really matter. I think that's true, right? That was just everything. You try everything, you do what works best. I mean, the number of experiments that can be run is insane. So then what you do what we found works best is to basically train the coefficients by matching the time derivatives at every node point. So what you have, right, is that every mesh point you have a function value, and what you really want is the time derivative at that point, which is a function of the other variables from the PDE, and that's what our loss function is. It's the mean square error of the time derivative, but that's only thing. So you train it. Once you trained it, and when you're doing inference, then you simply go around the circle. So you simply just generate, now you have a time integration algorithm. Okay, that's the idea. Right. Okay, so I'll start showing results, but, oh, yeah. Okay, so the blue is the ground truth. It's just very high resolution. So this is 32 times subsampled from the ground truth. The orange is what would happen if you used the normal numerical method, and it just goes to hell. And the green is this method. So 32x, here's 64x. And the thing is that it just basically, it knows about shots. It's seen them before. It knows what to do. Okay, so let me now just turn this into numbers. Yes?
Well, how does computational cost of those two course grid methods compare?
Good. Okay, so this is an important issue. So computational cost. So there is something, let me go back. So, okay, so there are many things that should make you nervous, but this is you put your finger on a very important thing, which is that normally when you do numerical analysis, we know these coefficients. So, okay, so for us, we have to compute the coefficients by pushing it through a neural network. And there are a lot of operations here that you have to compute at every point. Okay, so there is a speed cost. So there's a real issue that for this to become viable, which at the moment it is not, right, that you have to get around the speed barrier. Now, the one thing that I will say, and if I'm not representing this, you should feel free to say something else, is that actually the same thing is true for your phone. Right, so this is actually a well-known problem, right? That is that you need to basically make models that are accurate and small because you don't want to spend compute on them. And so, for example, in the computer vision, if I just go back to this super resolution problem for images, so it turns out that I showed you the neural net thing, but what I didn't tell you is there's a much faster way of computing the same thing without using a neural net, and that is the idea is that what you use is a bank of linear filters. So what you do is in every box, you basically, you have, suppose I have 200 linear filters that are all different. I just look at the box and I make a couple of coarse measurements and say, gee, which linear filter should I use? You just have to make one measurement. And then you do that, and then that's much faster, and then you've got the speed back. So that's one answer to this question. And we believe, and we have reasons to believe that this is not going to be a problem in the end.
No, this is already, we already compete.
Yeah, but we're already good. But we're already competing because we've coarsened the mesh to such an extent that, and this is only one dimension.
But it's like you're also not using compact stencils for the spatial derivatives.
We are using compact stencils.
You are using
Oh yeah, we are using compact stencils.
And how do you find the width of the stencil?
It's a hyperparameter for you to optimize when you do all of your choices.
You also should probably mention the constant coefficient.
I am. It's on the next slide. I'm going to talk about constant coefficient. Yes.
Don't you just pre-train? You pre-train on a set of solutions for the equation that you care about. So once you pre-train for that equation, you can generate novel solutions for that.
Okay, so this is bootstrapping. Okay, let me just make sure I understand. So remember, what we're doing is we're using the fact that your big solution local. Take the derivatives as local. So we only have to make sure that all local things are in the training set, right? We don't have to represent all local things because we're just doing little local things. And then the computer, actually the PDE will tell you how to piece them together. Yeah.
So you're doing two things here. One is the function f, and the other one is the derivatives, right? And the loss function is something I believe at the end.
No, the loss function is the way that you determine these constants C when you're training. So there's a training loop where you basically have generated your large set of solutions.
But you're thinking about those derivatives as being derivatives,
Yeah.
right?
Yeah.
But you're not really evaluating the pattern. You're approximating to the derivative.
Right, but you could. So we've experimented with all. You could, if you wanted, you could make your loss function demand that you're getting derivatives from. You could do whatever you want.
Right. But what you're thinking right now is that those C's will be some sort of approximation of derivative. But really, that derivative, you may be thinking that your first derivative is in there, but it's not.
Yeah, but it's pretty good actually. It turns out it is okay. I hear you. It's not explicitly coded, hard coded to use the loss functions, but it could be. My point is, so I guess maybe I want to say this. We should talk about this after, so I don't want to take up too much time on this. But let me just say that there's a huge amount of flexibility in this framework and many different parts of the framework, and we really tried some approximation of everything because we had access to this massive computing resources. What I'm about to show you are things that work. I would think there's no claim that this is the best that you could do, or even that this is the right thing to do. We are simply trying to demonstrate that this is possible. Is that fair?
That's the polynomial accuracy ensures that it is.
Yeah, that's true. We're also imposing polynomial accuracy, which is ensuring to some extent that it is representing derivatives. That's a good answer. Because if you, let's talk about that.
I'm assuming you're enforcing zeros for first order consistency, right?
Yeah, that's
If
polynomial.
you constrain everything,
That's
you
right.
can't
That's
do
why that's polynomial. And that's just a projection. That's basically enforcing constraints among these coefficients, which are enforced as part of the algorithm. Okay. Okay. So this is a quantitative evaluation of this for Brenner's equation. So this is the mean absolute error. I want to basically be clear about what this means. So this is the distance between the integrated solution and the ground truth. The ground truth is the high resolution solution. This is both the space and the time average. That is space and time average, meaning that it's integrated over all space, and it's also integrated over all time, less than some number. And it's also, and I want to be very clear about this, that because we're doing it this way, we can train on a small domain, is that you can simulate them accurately. So this is the idea, this is what we've been trying to do. And since you can simulate them, because we can solve Maxwell's equations, like I said, that was one of the 2 equations that we care about. Maybe more. So you use the simulations to create a training set. You then train a neural network on the training set, and then you use the output to interpret the experiment, and replace Crick with training on data, both are equally important. And then there's another important step, which I don't have time to talk about. We've been doing this in a specific example having to do with imaging colloidal clusters using holography, which is something you can simulate, is that then you have to, and this is when it gets actually interesting, is you have to make a noise model of the experiment. Because any experiment has noise, you can't actually simulate the noise. So then you actually have to go into the experiment and create noise models and figure out how to accurately corrupt things so that you don't get. And so it actually becomes a really interesting project. That's what I was going to say. It's not like just, this is not like clean and nice, but it does seem like there's room. So anyway, and it involves PE, so it was in this talk, and I'm now done. I'm going to stop. Thank you.
Floor is open for questions. So we know Maxwell's equations and Navier-Stokes. Those are the 2.
Well, maybe there's another one.
Schrodinger, maybe.
Oh, yeah, there's that. That's right.
Okay.
That's important.
Other questions? Yeah.
Do you have any slide behind this? Do you have any example that I'm trying to do?
Yeah, there are lots of slides.
Can you show some basic code with an example how it is?
Well, I can show you what we do, but this is.
You're thinking an answer.
I mean, basically, so we have, so Ellen, who's this graduate student of Ellen, she has this experiment where she puts colloidal particles in a well. So these are particles that are put in a well, and the particles stick to each other through some interaction, and she puts 10 of them in a well, and they bind with some probability, because there are thermal fluctuations, and then there are lots of different structures you can see. And her question is, can I basically characterize everything that happens inside of this box? And so it turns out that under optical microscopy, it's very difficult to actually distinguish things. And so instead, she uses holography. Actually, I don't realize this. Sorry, this wasn't very well organized talk. So instead she uses holography, and so holography, what you do is you send in light and you basically interfere the incident light and the scattered light with itself to create a hologram. So you end up with a picture that looks like this, and then you have to interpret the picture. So we've been basically training machine learning models based on simulations of holograms to try to reconstruct what the answer is. You follow the lines that I just said. There are many more slides, but that's the problem we've been working on. Admittedly, this is not the greatest problem, but it is at least a start to learn how to do this, and I don't know. I can tell you more, but I don't want to bore everyone because I feel like I've talked too much.
So I have a question on part 1. So you talked about patterns being equation specific, but you can imagine that a lot of the things you see in PDEs, fronts, waves, spirals, like these are canonical things that happen, and you can almost say, let me look at all the PDEs I've seen, put it all in, and could you just say, these are my bases for this? So now I build my catalog, and you probably thought this, right? That you say, actually, I could work across PDEs because, frankly, there's these structures that are canonical, whether it's wave propagation fronts. This equation might not have fronts,
so I think one thing, maybe you'll have a difference. So we haven't had the courage to do that yet. It's not.
It breaks down and we change the viscosity of.
No, but I'll tell you a version. But it breaks down. But there are things we haven't tried though. So let me give you an example. So I think that's very interesting. So do you know that there are translation systems? I'm going to answer this with another example. Okay, so the way the translation works, right? You put words in one language and you get words in the other language. So there are actually translation systems which are actually quite good that are trained on all languages. And then what you do is you have to put in a token, though, initially about what language you're translating to what other language. And if you do that, actually, it works. It's pretty amazing. It's sort of like this. So you can imagine tokenizing the input with something about the equation. And the reason, people told me this, I was like, seriously? And then they say, well, but that way you learn things because there might be some sharing. This is sort of what you're saying. So I think this is not impossible, but at the moment, we just want to change the way PDEs are solved. We don't necessarily need a universal PDE simulator. That was a joke.
That was a start.
That was a joke. That was a joke. That was an overly ambitious statement. It was never a joke. I just want to make sure everybody wasn't taking that seriously. I mean, it is what we're trying to do, you know.
More questions? Anybody else have some? Yes, Cam.
Just curious about, so you're saying to do the PDs and you have to feed in tons of data, right? It has to be representative. Do you really think it's generalizing in the sense like this machine translation will generalize, or is it really just seeing an example of everything and learning that?
So it is learning things. So I guess everything like I don't know. I told you everything I know. It seems to work. You've seen like if you do a small domain, it goes to a large domain. That's what I know. Okay. I think what's reasonable, what's physically reasonable actually, and this is the reason I sort of believe in this, is that physically we know that there are small scale structures. There are spirals, there are fronts, there are things. And physically we know, like, for example, if you solve Berger's equation, we know it's all about shots. We've known that for a long time. But the trick, of course, in simulating or solving is to piece them all together at a large scale. And it seems totally reasonable to me that you would build a model that would learn the small scale, and then you piece all the small scales together, and you generalize the different large scale behaviors as long as the small scale stuff that is there is within the bounds of what you use in your training data. Now, if something happens in the small scales, which creates a small scale structure that's outside of your training data, the whole thing will blow up. We've experienced this, there's no doubt, right? So you do have to be a bit careful. It's not true that the small scale is independent of the large scale, and quite the contrary. But on the other hand, this is something that one can get right, and I would argue that that's basically what this whole effective equation business has been trying to do for a long time. So this is not a new idea in any way. We're just trying to implement it slightly differently. But having said that, there are no theorems, and I don't know. But I think that there's good physical reason to think that this is reasonable.
But if that's the case, you could imagine running this procedure, putting in information about the symmetry structure, the Hamiltonian, and the dimensions and so on, and reproducing phase diagrams. Maybe not quantitatively, but qualitatively.
There's a lot that you could imagine. Like I said, I think I'm not being humble. I'm making a joke when I say I'm being humble, right? Or not humble, humble's not the right word, unambitious. I'm being unambitious. We unambitiously just want to solve a single, if we could solve the Navier-Stokes equation at Reynolds number 20,000 using this with 10 times faster than it ever been done, we would be exuberant. Like, we're just trying to do that right now. That's it. That's our problem. Like, if we can ever do that, then we can talk about making a universal equation solver or doing these other things. But at the moment, I just want to do that. That's it. Is that?
But there are like reduced order marking methods, like projection-based methods,
Yeah.
that are also machine learning, and they also solve it 10 times faster.
Yeah.
But I think an advantage here is you have these local basis methods.
Yeah.
So.
This is a different way of doing it. So I don't want to, there's no massive plan. This is just I think it's a different way of doing something which people are trying to do differently. And I would also, again, emphasize this is one way of doing it, which we did, and I'm sure there are better ways. And this is just what we've been doing.
So there's a technical question here, but Marcus is also a non-technical question. So say that you can solve, the differential equation at that Reynolds number. Will the people that solve that differential equation at that Reynolds number with traditional techniques reject this, or will they throw it out the door, or will they be uncomfortable because they say, well, you just machine learned it, I don't understand what's going on in the black box? So what's your sense of how?
I'm not sure. I want to convince myself. I don't care. Look, there is a problem here. There's a lot of hacking. I showed you the console page of the different turbulence models that exist that people do. There are a lot of heuristics that can be replaced and can be replaced in a systematic way, and that's what we want to do. And there's as we were talking about before the talk, there is an issue with do you believe the results of simulation? There are always this issue. This is not going to go away. There's a core question here as to what extent can machine learning be used to essentially coarse grain small scale users. That's what one does after that is another question that we can talk about in the context of a specific problem. That's my.
And just to make a comment, I think it depends on what one's objective is, right? So if one wants to actually learn deep things about the physical mechanisms that are at play, you may or may not get there. But if all you simply want to be able to do is compute something that takes a long time faster to get a surrogate, right, that take answer that's good enough to be able to make some other decision where there's many different places down the road where you're going to be able to take that error back out, right, through other testing or certification. then maybe you don't care, right? Maybe the surrogate's good enough because you need to be able to run it faster, right? I mean, right now, modern high fidelity CFD is not in aerospace design cycles because it's just too slow. So the question is, if you can get an answer that's good enough and you can take care of what slop you left out in some certification or qualification process later, maybe this is good enough because it lets you make a decision faster. But if I actually want to understand the ins and outs of each contribution of the vessel function, maybe,
Yeah, that's the 99%.
Yeah, no, I mean, this is the point. This is meant to be a very, I mean, we'll see, you'll probably found it, but it's meant to be a very practical.
We're going to go ahead and adjourn to the coffee hour. Thank you so much, Michael.